Hi everyone! Last time we talked about using the trapezoid rule and Simpson's rule to approximate the integrals, right? So today let's talk about the error. Okay, so for trapezoid rule, if the function f is twice continuously differentiable on the interval a, b, then this is our true value, the integral, the definite integral, equals, this is the approximation using the trapezoid rule. That is the error. Okay, this is the true value. This is the approximation. And the error term is b minus a to the third over 12 times the second derivative. Okay, and for n subintervals, h equals b minus a over n. Then our true values equals, so you see this is the formula for the approximation using the trapezoid rule. We have h over 2 times, well, the endpoints f of a and f of b, we have 1 copies, and all the interior points we have 2 copies. Okay, so the error terms, this is the error terms in general. So keep this guy in mind. So far so good, everybody? Okay, so you can realize the error term here. We have h squared, and we have the second derivative of f. Okay, and eta is some number between a and b. So usually if we want to find the error bounds, we will consider the maximums of the f prime second derivative over the interval a and b. So for the Simpson's rule, we require the function to be 4 times continuous differentiable. It means we required the fourth derivative of f exists. Okay, and if n equals 2 subinterval, we have, this is the approximation, and this is the error. But in general, the formula for the Simpson's rule, we have h over 3 and then times f of a and f of b, we have 1 copy. For the interior points, the coefficient is going to alternate between 4 and 2. So it's going to be 4, 2, 4, 2, 4, 2, 4, 2, 4. But it starts with 4 and ends with 4. Then it alternates inside. Okay, so what is the error in this case? So the error is b minus a times h to the fourth over 180 times the fourth derivative of f of eta. Eta is some number between a and b. So if we want to find an error bound for it, then we will look at the maximums of the fourth derivative of f over the interval a and b. So far so good, everybody? By the way, this error term, this whole formula will be given in the exam, so you don't need to memorize it. Okay? Alright, let's continue. Example 4. For each of the following, use the information given in the table to determine the minimal number of subintervals needed to approximate integral 1 to 4 f of x dx to within 10 to the minus 5. So here we're given the maximum bounds of f prime, and f prime, and the fourth derivative over the interval from 1 to 4. So we just need to pick the information we need. And here we don't know, we don't have a formula of f, so we don't know what it looks like, but we have the bounds for the derivatives. Okay, so part A, use the composite trapezoid rule. Okay, so what is the composite trapezoid rule? Here we have, let's see. Okay, so here we want to use h. So what is h? H is b minus a over n, right? And b is 4, a is 1, and n is n. We want to figure out n, so it's a variable. Okay, so in this case, that is 3 over n. What is the error term in the trapezoid rule? Okay, For the trapezoid rule, the error term is equals, okay, let's go back. So b minus a times h squared over 12, and then times the f prime prime. Okay, so this is absolute value of b minus a times h squared over 12 f prime prime of eta. Eta is a number between 1 and 4. So this guy will be less than equal to, well, because b is bigger than a, so we have b minus a, h is positive, so all of these guys are positive. And then the second derivative is going to be less than equal to the maximum f prime prime of x, where x is between 1 and 4. Now we're ready to plug in. B minus a, well, that's 3 minus, that's 4 minus 1, right? H, so over 12, h squared, h is 3 over n, h squared is then 9 over n squared. Is that okay, everybody? H squared is 3 over n squared, so it's 9 over n squared. Maximum of second derivative. Second derivative is 7. So let's simplify it. Well, this is 3, and this is 9, this is 7, and 12, and n squared, right? This can cancel. We get 9 times 7, 63 over 4n squared. So we simplify it. We want to control this error within 10 to the minus 5. This is what we want, right? And we want to solve for n. Well, how do we solve for n? I should write smaller, then I can have more space here. Let me see how can I change it. Okay, I have make it smaller. I hope that you have more space. Okay, so how do we solve for n? We can both sides multiply by 4n squared. Then we get 63 less than equal to like 4n squared times 10 to the minus 5. We can both sides multiply by 10 to the 5th. So then we get this. Right? Because 10 to the 5th and the 4n squared, they're both positive. We don't need to flip the inequality. Right? Then the n squared is greater or equal to divided by 4, right? 63 times 10 to the 5th over 4. Then n is greater or equal to, we can take the square roots. 63. Why we can do that? Because n is positive. Right? So that's why we only need to consider the positive square roots. Otherwise, we have to consider maybe x less than negative square roots of the things, or x is greater than positive square roots of those things. Alright, so let's calculate what these numbers are. So, calculators, we have square roots of 63 times 10 to the 5th, and then divided by 4. Okay, and the answer is 1254.99. What is the minimum n? N is an integer greater or equal to these number. Oh, 1255, right? Wow, 1,255 iterations or subintervals. Well, that's a lot, right? Okay, let's look at the Simpson's method. So in this case, h is still the same, right? H still 3 over n, but the error formula is gonna change. So what is the error formula? Let's go back. B minus a times h to the 4th over 180, and then the fourth derivative of eta. So b minus a, h to the 4th, 180, the fourth derivative of eta. Well, that's less than or equal to b minus a is positive, h is positive, 180 is positive, and then the fourth derivative is less than or equal to the maximum error, the maximum bounds over the interval of the fourth derivative. So even though the problem gave us the first derivative, second derivative, third derivative, and the fourth derivative, we actually just need the second one and the third one. Okay. So let's see. Let me do it here as well. So that equals 4 minus 1 times h. Okay, let's do it later. 180 down there. H to the fourth. So h is 3 over n. 3 to the fourth is 81. And then n to the fourth at the bottom. 50, and the maximum bounds is 15, right? Okay, what is that number? 4 minus 1 is 3. Wow. And 81. Okay, 180, we can divide it by 9. Right? 9 is a common factor, then we get 20 here. We have 9 left. Oh, we still have 15. So on the 15, we can also cancel it. And cancel the 5. So on the top, we have 9 and 3 and 3, that is 81. The bottom, we have 4n to the 4th. So far, so good, everybody? You don't have to simplify it, but you just have more numbers to calculate. Okay, we want this number to less than or equal to 10 to the minus 5. Alright, let's see. This is the same as we multiply both sides by 4n to the 4th, and we can multiply both sides by 10 to the 5th, right? And then n to the 4 is greater or equal to 81 times 10 to the 5th over 4. Well, n is greater or equal to the 4th root. 81 times 10 to the 5th over 4. Now let's see, what is this number? 4th root of 81 times 10 to the 5th divided by 4. Okay, so the answer is 37.72. And what is the minimum number of n? 38. Ooh, now you see the difference between trapezoid rule and the Simpson's rule. Trapezoid rule, in order to control the error bounds to 10 to the negative 5th, trapezoid rule, you need 1,255 subintervals. But the Simpson's rule, just 38 subintervals. Whoa, so quite a big difference, isn't it? Okay, let's continue. Yeah, so later on we will also use the MATLAB, and then I can show you like how many steps we can get the approximation within like some tolerance, and we can see the steps, the number of steps in the trapezoid rule and the Simpson's rule. Okay, let's continue. Example 5, to approximate this interval to within 10 to the minus 5th of the exact value, what is the minimum number of subintervals needed? So in this problem, we are given the formula of the function, and we're not given the bounds for the derivative. So we have to figure out the bounds for the derivative by ourselves. Okay, so let's do it. So our function f is inside the interval that is e to the 2x, right? And it's on the interval from 0 to 1. Exponential function is like this. So 0 to 1. So it is an increasing function. Do you see that? Okay, so in order to find the error, approximate the error for trapezoid method and Simpson method, we need the second and the fourth derivative. So let's keep taking the derivative. Well, derivative of e to the kx is k times e to the kx. So we have 2e to the 2x. And then when you take one more derivative, well, 2 multiplied in front become 4 e to the 2x. The third derivative, we multiply by 2 again, so 8 e to the 2x. The fourth derivative, we're gonna multiply by 2 again, so 16 e to the 2x. So far, so good, everybody? And because it's an increasing function, so the maximum of f prime prime x over the interval from 0 to 1 is f prime prime of 1. So we plug in x equals to 1, that's 4e squared. And we can tell this because f is an increasing function. We can say f prime prime is an increasing function, right? 4 times e to the 2x is an increasing function. So we just pick the right endpoint is going to be the maximum. Well, however, if you have a decreasing function, then the left endpoint, so the left endpoint is where you're going to get the maximum. So you have to be careful. Sometimes for the basic graphs, like a power function, polynomial, and all the 6 trig functions, exponential function, logarithm function, you need to know the shape of it. Okay, let's continue. We also need the maximum bounds for the fourth derivative. Oops. So in this case, we have the fourth derivative plugging 1, that's 16e squared. So far, so good, everybody? So n in this case is b minus a over n. B is 1, a is 0. So that is just 1 over n. So trapezoid method. Okay, so the error, if you can remember, if you don't remember, it's okay. I'll provide that in the exam. So b minus a times h squared over 12. And then, we can actually, okay, let's do, okay, doesn't hurt to do one more step. We know that is bounded by this guy and maximum of the second derivative, where x is between 0 and 1. Okay, so far so good, everybody? Okay, b minus a is 1. H, okay. H is 1 over n, so h squared is 1 over n squared. And then we have the bound, the f prime prime is 4e squared. Oh, we can cancel this. We get e squared over 3n squared. And we want this answer to be less than or equal to 10 to the minus 5. So both sides multiply by 3n squared and multiply by 10 to the 5th. This is what we get. And let's see. Okay, good. We still have a lot of space. So we have then n squared is greater or equal e squared times 10 to the 5th over 3. So n is greater or equal to square root of e squared 10 to the 5th over 3. So what is this number? Square root of e, where's e? Here's the e square. And then 10 to the 5th. Oops! You see what happened? Yeah, we gotta go down. E squared. Oh, okay, let's redo it again. E squared. Oh, okay. And then did we go down already? Yes. Oh, we did not go down already. So let's go down. Let me redo it. So e to the 2. Last time I put a square, it should not. And go down. Times 10. What happened? Do I need to put times? Oh, yeah, I do. 10 to the 5th. Over 3. Okay. And That is 496.3. 496.3. So the minimum n is 497. Equals, even though it's 0.3, we should need to round up because we're looking for a number that is greater or equal to 496.3. Okay, so that is the trapezoid method. So by the way, all of these examples, I hope you can try it first and then continue to play the video to check your work. Okay, so the error term is b minus a h to the fourth over 180. And then this is the fourth derivative of eta. b minus a h to the fourth over 180. That is the maximum. X is between 0 and 1, the fourth derivative of x. So what is that? b minus a is 1. H is 1 over n, so h to the fourth is 1 over n to the fourth. And then the maximum of the fourth derivative is 16e squared. We want this number to be less than or equal to 10 to the minus 5. Okay, let's see. We can both sides multiply by 180 n to the fourth. We get 16e squared, 180 n to the fourth, and we can both sides multiply by 10 to the fifth. Right? Then we have n to the fourth greater equals, and then here we have 16e squared 10 to the fifth over 180. So n is greater or equal to 4 root 16 e squared 10 to the fifth over 180. Okay, let's plot this number in our calculator. So the 4 roots of 16 e squared, and then come down, oops, times 10 to the fifth, oops, to the fifth over 180. Okay, 16.009. Even though it's so close to 16, but you still need to pick one number. Yes, 17. We're looking for an integer that is greater than or equal to 16.009. So far, so good, everybody? Well, you can see, well, trapezoid method, 497 subintervals. But Simpson's method, only 17 subintervals. Yeah, so Simpson's method is like more, more accurate. Okay, so right now, let me teach you how to use MATLAB to compute. Okay, so let's approximate this interval. By the way, you know we're not able to integrate this integral. Do you? Do you know that? So we can integrate e to the x dx. Yeah, with this one we can integrate. We can integrate this guy by integration by parts. We can integrate this guy. If there is x there, we can integrate this by u substitution. But without an x, this guy, we're not able to integrate. Okay, but now we can use numerical integration to approximate it as close as we want. So first, let's use the composite trapezoid rule with n equals to 10 subintervals. The syntax is I is like the interval equals trapezoid, and then f is the function, the integrand, right? And then we have a is the left endpoint of the interval, b is the right endpoint of the interval, and n is the number of subintervals. Okay, so it inputs trapezoid, inline the function. So here when you type exponential function, you have to type exp parentheses minus x squared parentheses. Okay, and then the left endpoint is 2. Sorry, the left endpoint is 0. The right endpoint is 2, and then equals 10. And then after you input this in MATLAB, you can see the answer is 0.8818. Okay, and if we do the same thing using the composite trapezoid rule with n equals 10 subintervals, well, the answer, so you're going to replace chap by simp, Simpson's rule, and then you get the answer is 0.8821. Okay, so in order to compare like which method is more accurate, let's type in when n equals 100. You can see the answer is 0.8821. So we know the Simpson's method is more accurate to the true value, and the trapezoid method compared to the Simpson's method is not that accurate. Okay, compared to it. But 8818 is still good enough, right? The answer is 0.8821. Okay, so let me show you how actually we type it in Octave. Okay, so this is the Octave. Make sure your folder contains our M functions folder. Okay, and then here let's input I equals trapezoid inline functions, and then exp minus x squared, and 0 is the left endpoint, 2 is the right endpoint. Let's do 10 subintervals. Okay, let's see. Okay, it turns out I missed a parentheses. So yeah, it turns out last steps I have no parentheses on the right, so there's a problem. So what I need to do is I need to insert here the parentheses. Sometimes you have to be okay. Alright, then here is the answer. Okay, so the approximation is 0.88184. If we increase the number of subintervals, like do 100, ooh, see, we have 0.88208. If we use Simpson's method, let's replace trap by simp. That's the Simpson's method. So see, the answer is 0.88207. And if we increase, let's say, 100 steps, yeah, you see, we get 0.88208. So now we can see the Simpsons method, even though we only use 10 subinterval, but we already get 0.88207. However, for the trapezoid method, we only get 0.8818. Let's see. If we get 50, then we get 0.88207. Okay, so then we know that trapezoid method, and compare with the Simpson's method is more accurate than the trapezoid method because it use quadratic polynomial to approximate it, and trapezoid method is just like secant line. Okay. So that is numerical integration. We talk about two methods, Simpson's method and trapezoid methods. We also talk about the errors. All right, so please do your homework, and when you have questions, please ask me. Cheers, have a good day. Bye.